So, welcome back to another class on the speech processing course. Today, I'll just briefly review what the different architectures. Specifically, we are going to look at mostly what we call a sequence to sequence problems, right? Because speech is a sequence of we are saying a sequence of sounds which form words, and then from words we form sentences, right? And so in the speech signal we don't know what is being said, so we concatenate, or we take a sequence of what we call as frames, which is nothing but windowing speech for 25 milliseconds, finding out the features for that, then moving by another 10 milliseconds, then finding it out, moving the window by another 10 milliseconds, finding it out. So we get a sequence of acoustic information in terms of spectra and so on, okay? And that we are directly converting. Remember, we used to talk about going to the phonemes and then using lexicon to words and then using language model. What we normally do is now what is called end-to-end speech recognition systems. So we want to bypass the knowledge that a lexicon is necessary. I mean, to prepare a lexicon, we often depend on phoneticians, especially in English. In most Indian languages, what you speak is pretty much what you write, okay? So there the lexicon creation is a little more easier, but nevertheless we from inspired by what Alex Graves and CTC and all of these, we directly go to characters. In fact, we don't go to words because the set is too large. The characters are about 30, so the outputs have to be one of these 30 characters. When I say 26 for English, plus 3, 4 for punctuation and all that. If you talk about Hindi, it might be 45, 50 and so on, okay. But we can also go to an intermediate step called the byte pair encoding. I will not go into the details. So that is like taking a sequence of taking 2 characters at a time or 3 characters at a time that occur quite often, right. These BPEs are inspired by your compression algorithms that are used in, for example, text compression, right. So you have a huge file, you compress it, right. So the basic idea is some of these sequences occur very often, right. So if there are 3 or a 4 word sequence, that means they are going to occupy 4 characters. Each character is represented by some binary representation, right. So if you merge all the 4 and use one code for it, right, one symbol for it, right. So every time that 4 characters get replaced by only one symbol, then that is more efficient. Basically that is the idea, okay, of compression. But we are exploiting it because in speech or in text you will see that is, the, are, am occur quite often, right. And so you don't want to separately recognize a and am, and so it might become am, So you see in the language itself that these occur very often. So it's somewhat capturing sequences that occur quite often, and therefore some kind of knowledge is built into it that these are probably THE is often occurring together, and so it is sort of like a character language model which tells it that it is more appropriate maybe to put THE there rather than separately recognizing T, H and E, and you might make mistakes in that, okay. So now this class, it's more animations. We have borrowed a lot of things from web. It's all taken from the web. It's done by my students, Vasishta and others, and hopefully we have also acknowledged or credited where we are borrowing from, but it's more like giving you an intuition through these animations what happens in sequence to sequence modeling, okay. So so it's more of the RNNs, right, because RNNs are the ones that are very good for sequence to sequence modeling, right. So typically, remember, RNNs have 3 aspects, right. One is the input layer that itself has multiple nodes, but I am representing it with one large red circle. Then there is a hidden layer which has itself multiple nodes, that I am large blue circle, and the output is represented by a red circle, black circle here, right. That also might have, depending on the number of classes and so on, many nodes, okay. Now this is a feed forward network, okay. So there is no feedback that is coming here, right. So it is going in only one direction. So this becomes a feed forward network, right. But if I give a feedback here such that, and as I progress along time, the output of the first is going to be fed back for the next input, output of the second will be fed back when I give the third input, output or the third will be given as feedback for the fourth, then it becomes a recurrent neural network. Okay. So, we are taking the output of the hidden state and feeding it back as an input for the next input itself. So, this is a sequence information. So, we most often sequences here we are talking about is in terms of time, or if you are talking about words, that in the order in the words will occur. Okay. So, the first word, second word, third word. So, there is a sequence that you are going to get, right. So, so in recurrent neural networks always two inputs start coming. In a feed forward, this is the input, this is going to the hidden layer and output comes, right. So, there is no dependence on the previous input or the future input. In recurrent neural networks, you can also look at future inputs if you are looking at the other direction. So, sequentially they are going, and so you can go from left to right or right to left. That means you start from the future samples of future words or future events and try to predict the previous word and so on. Okay. So, that is the basic idea of a recurrent neural network. So, it is useful for sequence modeling, and you can see that I have discussed not in any detail that RNNs generally have this problem of something called vanishing gradient. Actually, we have a slide that shows beautifully what that is, right. But we will have this idea that that we have to use something called long short term memory or LSTM, which basically will help overcome these problems. Okay. So, what is happening is, so I am feeding here some input, right. So, these are the inputs, but each one at a time there is a connection coming from first of all it is processed sequentially, that is each of them are, they are not going parallelly. You can see first guy will come, then second guy, then third guy, then fourth guy. So, it is doing it fast, but you can see it is sequential. This is going to be a problem as I pointed out, and the next topic itself, the transformers are going to handle this issue of sequential nature. So, once I do sequential, I have to wait for each previous guy to finish before I go to the next guy, and that is going to be time consuming, right. I cannot, while the first guy is going, I cannot feed the second guy, I have to wait for the output of the first guy to come. That is a big problem in RNNs. Okay. So, we will see here that that is going to be solved by the transformers. The next issue is the fact is that we need to carry this information through long distances, right. So, if I am saying I was born in Assam where I did my schooling, therefore, I speak Assamese, this guy Assam is going to be affecting Assamese many words later, right. And so, when I am going through the sequential nature, we are going to have the problem that the words, if they are very far apart, the influence is going to reduce. Okay. And one of the reasons that that happens is because also the reason why this vanishing gradient and exploding gradient problem is going to come. Okay. So, we are going to so the LSTM avoids that problem, but we will see what is happening. Okay. So, why is this when I am going over sequence which are of longer lengths, what happens to the effect on the last guy? Let us see. So, if I am saying, so this is there is a one speech, then there is a text processing. What does speech processing, let us say speech recognition do? It converts speech to text, but I have to do something useful with the text. For example, I am having this device Alexa, right. Alexa, what is the time, I am going to say, right. And Alexa is going to recognize, the device is going to recognize the words, what is the time, right. So, it is converting speech to text. Now, it should know what to do with that particular text, right. So, it has to know what is called intent of the person, why is he asking, right, because I can ask anything under that, who is the Prime Minister of this country, what is the weather, right, and for each one of them it has to go and search appropriately. So, when I am asking about time, it knows that I am looking for what is, then it is going to go into the domain of time. So, that is the intent, right. If I am trying to find out what is the weather, it is trying to find out that the intent is to find some weather information, or who is the Prime Minister, the intent is to find some gender knowledge, or play some Jawani Diwani song or something like that, So, it has to know that means you are asking it to play some particular song, and it has to go into the domain of songs. So, the intent is that I want to listen to some music, right. So, I have to process, and that is called intent detection, right. And then it has to also have databases from which it can fetch all these things and properly do, right. So, if you look at only the first part, right, it is what time is it, right. So, if when I am going to do something like this, what is the first word I am saying. So, it has to, at this point it has a large influence because that is the only word coming. When I say time, time is in a different color. So, you see that both of them contribute at the output. If I am looking here, both of them have some contribution. What is quite nearby, and time is also there. When I come to is, which is more like orangish color, the effect of what has already started decreasing, and time is also decreasing. So, I mean, this is illustrative, okay, it is not exactly the way that it is happening, but to give you an intuition, why some things happen the way they are happening. So, when I look at the last question mark, if I take question mark is also another word, the effect of what is disappeared, right. And that is also the problem when I am talking about connection between long distances between I grew up in Assam where I did my schooling, and therefore I speak Assamese, right. So, what happens is Assam is a key word for Assamese, but if it is far apart, the influence is very little. So, often that is an issue with RNNs, okay. So, once I do that, this text that I am taking, this output is usually what we feed for the intent detection, and it is going to say ask for time, okay. But by looking at this output itself, you can see that time is an important idea, but that is going to be having a very small role here, right. Time is almost what and time are very important ideas, but almost in the intent detection it is not going to be playing significant role if I take output here, right. And that is also the reason why we have about the problem of vanishing gradient and exploding gradient, okay. So, the final RNN is very little influenced by things that are far up at a very great distance from where I am looking for, okay. So, as I said, what and time are very important for me to understand the intent, right. So, what is the problem of the vanishing gradient? Vanishing gradient, so if you remember, what is the gradient? Why do we require gradient? Remember, in neural networks we are adjusting weights. We start with some random weights or some, somewhere we start some initial point, then we keep adjusting the weights to improve our prediction or our fitting of something, right. So, how do we improve, how do we adjust the weights? Remember, I told you it is using a very simple idea. That initial weight or some present weight is there, it is going to be altered by a small amount using this learning rate. So, the learning rate is going to influence how much you want to change the weight and get a new weight, multiplied by the gradient or the slope. What is the slope? Remember, if you go back and see what I talked about in back propagation and how do you improve the weights to reduce the error. So, if you plot the error versus weight, it will be some kind of a curve, right, and we want to pick up the minimum error, right. And so, the gradient tells you which is the correct direction in which. So, if it is a positive gradient, it will try to move to the right, if it is a negative gradient, it will move to the right towards the minima, and if it is a positive gradient, it is going away from the valley. So, it will push it back towards the valley, towards the minima, right. So, there are 3 steps in any in the learning step. So, first you forward pass the entire data, right. It is a batch of data, that is, we take a collection of data and send it across. Then I compute the average error across all the batch that we have. Then once I compute the error, I am going to use derivative or the gradient with respect to the error and some chain rule, because I will have multiple layers and so many weights. So, I have to apply the chain rule to come to the lower layer weights of the lower layer, okay. And what will happen is that as I am progressing, so this is a forward pass. So, I start from somewhere and finally, I go to the end where I do the prediction and then some error will be generated. I use the error to back propagate and adjust the weights. Okay, and in doing so, what happens is when I go further down and down and down, the effect of the gradient is going to get smaller and smaller and smaller, but it can actually vanish itself, that it does not do anything, it does not adjust the weights at all. If the gradient goes to 0, then it just what, so W minus eta, which is the learning rate, times 0. So, it is not going to adjust the weight at all. On the other hand, if the gradient starts exploding, then the eta times the big gradient, big slopes are going to come, and so the weight will jump by a large value, and that might be harmful also. It might go off into some other region, and so you might even get out of, even though you are in a proper minima, near a minima, the weight adjustment may make you move away from the minima. Okay, so the exploding gradient is also a big problem. Okay, so the vanishing gradient, basically the intuition is the gradient keeps reducing as you go through time. Remember, if I am talking about RNN, it is a sequential kind of a structure. So, it is back propagating all the way, and then with all this feedback, it is going to get very, very small. Okay, that could be possible, right, and the other is the exploding gradient, which will make it very large. Okay. So, both of these are solved by using this idea of LSTMs, that I am not going to go in great detail here, simply because it is too much ideas. I am only, at a BSc data science course, you want to understand the big picture, right. If you are interested in the details, you can go and look at these, but basically as I said, there is a way that whatever information is important, it tries to preserve that. What can be forgotten, it tries to forget, and then it keeps passing something that is important through many steps, so that even if the distances are far apart, it does capture the Assam part and tries to move it forward. Okay. So, this is done by Schmidhuber and group. There is also GRU that I am not going to talk about in detail here. So, this input gate, cell state, all these are very, very important ideas, which I am not going to talk about. And here what we are talking about is where are sequence to sequence kind of ideas used. They are now pretty much used in almost many applications. So, for example, translation is a sequence to sequence problem. So, originally people were trying to do statistical approach. What is the idea of translation? That given some English text, I find let us say Hindi text which is best kind of translation for this particular English sentence. But remember, translation is not it is not very easy to measure the quality of translation. If you look at two translators, humans themselves, I can translate, see again it is like message. I want to say, do you want to go for lunch, right? I can say that in many different ways. Want to go for lunch? Do you want to go for lunch? Lunch, just lunch and a question mark, lunch. That is actually my prosody, my pitch itself is lunch. So I am changing, and that itself is like a question mark, right? Or hey Hari, you want to go for lunch? So I can say in many, but the message is only one thing. Do you want to go for lunch, right? Or even I'm hungry. You want to go? So I am not even using the word lunch. Okay. So if it is lunch time, you know that I am calling you for lunch, right? So there are many, and all of them are valid, right? So even here, even if I give a sentence in English and I ask them to translate to Hindi, no two translators will agree more than if you do an analysis. Most of the time it is only about 50 to 60% of the time exactly the two Hindi sentences will match. It is amazing. It is so different. Okay, each translator has its own way of doing, because even we, right, we have our own favorite way of creating sentences, right. We all speak English, we all speak Hindi, we all speak Tamil, we all speak Kannada, whichever language we know, but the same thing, it's not always we say the same sentence, right. So we are always creative, we create so many different sentences, but the meaning often is very almost the same meaning we do, and that's what makes it very lively, right. Otherwise, if everyone says the same sentence, it will become boring, I think, life, right. So this is all creating some richness. Okay. But in therefore, first of all, evaluating translations are very, very different. They are difficult. They use something called BLEU scores, BLEU. It's only approximately they are finding out how many words are matching. First single words, how many match in pairs of words, how many of them matching. Try these, you can see pair words, 3 words, 4 words. You immediately remember that these are related to our bigram, trigram, 4gram and so on. Okay. So, we are only looking at a weighted combination of these things, how many times, how many unique words are matching, how many words, combination of 2 words are matching, right. So, BLEU score is some kind of weighted combination to measure the accuracy of the translation. It is not perfect, like as I said, I might not even use the word lunch and still I might imply what I want. Okay. Machine translation therefore is the task, is a sequence to sequence task. Given a sequence of English words, I want to convert it to a sequence of Hindi words. Last class we talked about the encoder-decoder. I could use CTC, but it is a little more cumbersome because remember that in CTC, first of all, the output length cannot be more than the input length, and often there is some kind of a monotonic relationship that is assumed, whereas in attention, how are you and aap kaise hai. So, aap is actually mapping to you, and those are very, very opposite, right. You is coming in the last here and aap is coming in the first, the word order itself is different, right. So, so measuring translation is not easy, and training it is also is something that we are, how are we going to train? We are saying this is an English sentence and this is the Hindi sentence, you learn from it. This Hindi sentence, one of the translator has given us, right, while training, right. Whether that is the best, I mean, there is no best, right. So, some other translator could have given something different. So, it is learning, and that is why if you give many translations for the same sentence, it learns to generalize and do many things. Okay. So, and language models I am not going to go, we already dealt with in many in great detail for the both the neural part and this is the n-gram language. Given some previous context like previous 3 words or 4 words, can I predict what is the 5th word, and you can write the probability of the sentence, right. This is used often in speech recognition. This is the language model. What is the probability of the sentence? The acoustic model is going to give me some sequence of sounds from which I create using the lexicon sequence of words, but how does the language, if I did not have the acoustics, if I am only using text data, what is the probability of this sentence that the acoustic model is giving? So, that is called shallow fusion. I will take the language model probability only based on text, what is the prediction that this sequence of words will occur, and the acoustic model is saying from the sound and based on phonemes converting it to lexicon and then words, I am predicting these sequence of sound, how well do they match. So, in the acoustic model there will be some alternate sequence of words, right, which are competing in terms of likelihood scores and all that, and then you merge with this score and that score and see which one maximizes the score. Okay. So, again this is a translation example with an encoder-decoder. This is suggested by Badano, and actually again you can see I borrowed some material from Lena Wojta. So, right now what Badano did was, and we will come that we will replace this by something called transformers, had RNNs, right, and so you will give a sequence of words in one language. For example, I saw cat on mat, right, and basically what happens in Lena in the, this is Russian by the way. So, this guy is actually going to feed sequentially. So, there is a feedback that comes. So, I saw a cat on and it is trying to predict the next word. 2 things go as input, right. Obviously, the encoder's state, what context vector comes in, as well as you can see that as I progress, there is some kind of a language model that is also being learnt. Okay. Language model of what? Language model of the translated language. Okay. So, this decoder you will see in practice acts like some kind of a language model. Okay. So, not only is it isolated language model, it is also taking some input. We will see later attention also comes into the picture. Attention also is an important role here, and so that which part of the input it should focus on. also the other part it's going to play is the sequential language model, and it's going from left to right only. There's no right to left because I don't know what you're going to say next, right? Although I have a full sentence here in this when I'm creating the sequence of words, I'm only creating word, second word, third word. So I have only history of the first 3 words when I'm looking at the fourth word. So this is called auto-regressive, right? And it's going to be sequential. And last class I said it's not necessary that I should have only one layer of the hidden layer in the RNN. I could have multiple hidden layers. The deeper the network, the better, right? And so we normally have a stack of 3 or 4 layers. Even the decoder can have a stack of 3 or 4 layers. Okay. So, there are 2 RNNs in the encoder-decoder architecture. One is the encoder RNN, the other is the decoder RNN. The encoder RNN, it sees the entire text, right, and then but it feeds sequentially because I have to generate the output for the first word to get the second word, So, even though I have all the data available, I am going to feed sequentially. In the decoder, I necessarily have to do actually when I am doing the training part, I can see the entire text. This is called beginning of sentence. We normally use SOS or BOS, start of sentence or beginning of sentence, and we have to tell the decoder to stop decoding because you keep on feeding it, it's a feedback, right. So, if I don't tell it, it will keep on doing it forever, right, and end of sentence can come, okay. And by the way, if I do this, actually that is the whole idea of what you will see later is generative pre-training, GPT. It can even given a large sentence, it can keep on writing sentence after sentence after sentence and even create big articles, books and all that, okay. So, yeah. So, I am not going to this is a repeat of what I said last class. If I feed only one context vector, that is not it's capturing everything about the sentence we hope, but we can ease the problem by feeding the same thing at multiple places, and then why not take the hidden states from the encoder itself and provide attention. So, that is something that is done here. The slide is quite detailed. I will not go into it, but attention mechanism basically helps you focus on different aspects. Okay. So, now I am going to talk about what's called transformers. Okay. So, maybe the attention mechanism is something that is useful. So, let me see if I can put it in a simple way. These are a little more complicated. So, remember this green is the encoder and this kind of purple is the decoder, and we have one context vector that is coming. But I last class also said the output of each of these hidden guys can also be helped, and then we are going to feed for each one of these a combination after combining these hidden states to each one of these to help improve, and they do improve the performance, right. So, this concept of attention comes here. So, what is the concept of attention? So, we are basically having hidden states coming out of the encoder, right, and this is a decoder. Let us take the machine translation problem. This will be the English sentence, and so I will get English words that will be converted to embeddings. Then I also have the by the way, this should be I don't know if why it's getting the same sentence, but this should be in the other language. Okay. So, the Russian kind of thing should be coming out here. What we are going to do is how do we combine these outputs, right, which is hidden state, to feed it here, right. So, why is this attention important, right? If you remember the example that I gave for Hindi, which all of you can understand, how are you, aap kaise hai. Now, aap should be focusing on you, right? Aap and you are very closely related. So, what we want is at every word, at every step that we are doing, we want some kind of a weight which tells pay attention to these words more than the other words. And so, this whole thing is a neural network which is called the attention neural network, which sort of learns how to weight these guys. Okay, so that is why we call this as an attention weights and attention mechanism. Okay, so I am not going to go into the details because I can spend a lot of time, but then it's not going to it's going to be too much details. Okay, but the important thing to remember is that if you have similar languages, let's say coming from the same family, let's say English and French, right, they have the same word ordering, right. And so if you look at this, the attention mechanism, it is actually going to, this word should focus on this word should, so wherever the whites are there, it is focusing on that aspect, and that is correct, because if you have the same language, you should know where it should be almost monotonic kind of relationship. Okay.